Welcome back, fellow carbon-based life forms, to another audio deep dive designed to distract you from the crushing weight of your student loans or the fact that your houseplants are definitely judging you. I am your host, Maple, currently fueled by 3 cups of questionable coffee and a profound sense of imposter syndrome. Why are you here? Why am I here? Presumably, we both have nothing better to do than obsess over the minutiae of the universe until our brains leak out of our ears. We're nerds. It's what we do. So grab your noise-canceling headphones, ignore that pile of laundry that is gaining sentience in the corner, and let's ruin something beautiful with overanalysis.
All right, let's get into it. Today's victim, the atom. Ugh, even saying it feels reductive. The building blocks of the universe. I hate that metaphor. It's just so lazy. Building blocks implies stability. They imply solidity. If you step on a Lego, it hurts. But the reality of an atom is so much weirder and honestly, so much emptier. Yeah, you see that number? That's how much of an atom is just nothing. Empty space. We're taught in school that atoms are these neat little solar systems, but that's a lie to keep children from screaming. It's more like this. If the nucleus of an atom was a marble sitting on the 50-yard line of a football stadium, the electrons would be like a few gnats buzzing around the nosebleed seats. That's why you never truly touch anything. You are currently hovering slightly above your chair on a cushion of electromagnetic repulsion. You're just aggressively almost touching things. Feel lonely yet? You're welcome. But the big question, the one that keeps me up at night staring at my ceiling fan, is about longevity. Do these little vibrating specks of existential dread actually last forever? Or are they just procrastinating their inevitable demise, much like I am with my taxes? It's a crisis on the femtometer scale, because if the fundamental stuff isn't permanent, what hope do we have? Let's dig in. Okay, every good investigation starts at the beginning. You have to trace the suspect back to its origins. And for every single atom in your body, the story begins about 13.8 billion years ago. We got to go back to the scene of the cosmic crime, the Big Bang. So in the very first moments, the entire universe was this unbelievably hot, dense point. And then, bam! All matter and all energy that will ever exist is created. It's so hot that nothing can really form yet. But after about 3 minutes, things cool down just enough for the first light elements, mostly hydrogen and helium, to get their act together. Still, it takes another 380,000 years for the universe to chill out enough for electrons to finally settle down and orbit those nuclei, forming the very first atoms. Now, I know this sounds like a wild story, but we have the receipts. The case for the Big Bang is built on some seriously solid evidence. Clue number 1. The getaway. We can literally see that all the galaxies are rushing away from each other. If you rewind that movie, everything has to start in one place. Clue number 2, the afterglow. We can detect this faint microwave radiation coming from every single direction in space. It's the leftover heat from that initial explosion. And clue number 3, the chemical fingerprints. The amount of hydrogen and helium we see out there in the cosmos, it perfectly matches what our theories predict. The evidence is just overwhelming. And we can even bring in a key witness, the legendary physicist Richard Feynman. He once asked this amazing thought experiment. If all of science was going to be destroyed, what's the one sentence you could pass down to future generations to give them the biggest leg up? His answer was basically this: the atomic theory. The idea that everything is made of these tiny, constantly jiggling particles is the most important scientific idea we've ever had.
So the Big Bang gave us hydrogen and helium, the simple stuff. But what about everything else? What about the carbon in your DNA, the oxygen you're breathing, the iron in your blood? For those, we have to look to the next stage of our investigation, the fiery hearts of stars. You can think of stars as these giant cosmic forges. Gravity is the hammer, pulling all that hydrogen and helium from the Big Bang together. The pressure gets so intense that it ignites nuclear fusion, which literally smashes atoms together to create heavier elements, all the way up the periodic table to iron. But for anything heavier than iron, you need something even more violent. You need a supernova. The explosive death of a massive star is the only event powerful enough to create and scatter things like gold or platinum or uranium across the galaxy. So let that sink in for a second. Every single atom of iron in your blood was forged inside a star. And since our sun isn't big enough to make iron, that means all the material that makes up you and me and the entire planet had to come from a previous star system that lived, died, and exploded long before our sun even existed. You are, quite literally, made of recycled stardust. All right, I need to interrupt my own spiraling mental breakdown for a moment of blatant capitalism and desperate validation seeking. Listen, if you enjoy this specific flavor of neurotic rambling, you need to feed the machine. The algorithmic overlords are hungry and they demand tribute in the form of engagement. If you're on a platform that has a subscribe button, smash it with the fervor of a proton smashing into a lead target at CERN. Leave a review that makes my parents question where they went wrong in raising me. 5 stars only. 4 stars is just passive-aggressive. Do the things. It validates my existence and keeps the lights on in this basement studio. Okay, we're back. We know where atoms come from now. So let's get back to our central mystery. Do they last forever? Well, the answer depends entirely on their stability. Some atoms are rock solid, incredibly chill. Others are a hot mess. So let's profile these suspects and figure out what makes an atom go bad. It all comes down to a tiny battle raging inside the nucleus. You've got all these positively charged protons crammed together, and they all want to fly apart. The only thing holding them together is something called the strong nuclear force, which is basically the universe's superglue. Neutrons are the key. They provide more of that glue without adding to the repulsion. Stable atoms have this perfect golden ratio of protons to neutrons. But if you have too many or too few, the nucleus gets wobbly. The repulsive forces win, and the atom becomes unstable. So an unstable atom will eventually try to fix itself. It decays, and it has a few options on the menu. In alpha decay, it just spits out a chunk of 2 protons and 2 neutrons, turning into a completely different, lighter element. In beta decay, it performs a kind of atomic alchemy, where a neutron flips and becomes a proton, or vice versa. And gamma decay is the simplest. The nucleus just releases a blast of pure energy to calm itself down. Now here's the crazy thing. You can never predict when one individual atom is going to decay. It's completely random. But if you get a big group of them together, they decay in this incredibly predictable way. This is where we get the concept of half-life. It's the amount of time it takes for exactly half of the radioactive atoms in your sample to fall apart. And that reliability is the key to one of our most powerful forensic tools. Take carbon-14 dating. While you're alive, you're eating and breathing, and you're constantly absorbing a tiny bit of radioactive carbon-14 from the environment. The moment an organism dies, it stops taking in new carbon, and a cosmic clock starts ticking. The carbon-14 it already has starts to decay, with a half-life of about 5,730 years. So by measuring the ratio of the carbon-14 that's left to the stable carbon-12, we can figure out almost exactly how long ago it died. It's pure atomic forensics. So the lifespan of an atom is just all over the map. On one end, you have these synthetic elements we make in labs, like tennessine-294, which exists for a grand total of 78 milliseconds before it vanishes. Poof! On the other extreme, you have something like bismuth-209. For a long time, we thought it was stable, but it turns out it has a half-life of 19 quintillion years. That's over 1 billion times the current age of the universe. But as you can see, there's one more suspect on our chart, the most fundamental one of all, the proton. Right. We've seen that whole atoms can change and decay. But what about their most basic parts? Could a proton itself, the very heart of an atom, have an expiration date? This is where physics gets really, really weird, and we approach our final verdict. Okay, some theories out there predict that protons do, in fact, decay, but their estimated half-life is 10 to the power of 34 years. I mean, that number is so mind-bogglingly large, it's basically meaningless. If you had been watching one single proton since the Big Bang, the chance it would have decayed by now is essentially 0. For all practical purposes, they might as well be immortal. So where does this wild idea even come from? It's from this ongoing quest in physics to create a grand unified theory, or GUT. Physicists really suspect that the fundamental forces of nature are all just different faces of a single underlying megaforce. Think of it like how ice, water, and steam are all just H2O. These GUTs predict that under the insane energies of the early universe, protons wouldn't have been stable at all. So let's circle all the way back to our original question. Do atoms last forever? And the answer is a deeply unsatisfying kinda. Yes and no. Some are gone in the blink of an eye. Others will outlast the stars themselves. And even their most fundamental parts, the protons, might have an expiration date so far in the future it basically is forever. You know that old saying, a diamond is forever? Well, it's not true. Give it enough time, we're talking millions or billions of years, and the carbon atoms in a diamond will slowly, inevitably rearrange themselves into the more stable form of graphite, the stuff in your pencil. The atoms themselves don't die, they just change their bonds, their form, their whole situation. So, do atoms last forever? The answer is a resounding meh. Pretty much, unless they don't. And even if they do, eventually protons might get bored and fall apart in about 10 to the power of 34 years. Sleep tight on that thought. All right, my brain feels like it's undergone significant alpha decay. I need to go stare at a wall. This episode was barely held together against the forces of entropy by the strong nuclear force that is our producer, FireflyHaku. Honestly, if FireflyHaku were an isotope, they would be lead-208, just absolute, unwavering stability in the face of my chaotic electron energy. We don't deserve them, and their half-life is definitely longer than mine. And thanks to you, the listener, for tolerating this. Try not to think too hard about the fact that you are mostly empty space holding a smartphone made of dead stars. Goodbye forever, or until next week, whichever comes first.